Let's see. Trivia stuff. What does the G bit do in a segment descriptor? Yep.
Specifies the granularity, whether it's 4K pages, 1 byte.
Yes. Good job. Yes, it specifies the granularity, G for granularity, and it says, is my limit in this segment in bytes or 4 kilobyte chunks? How about the L flag? It's got the L flag. Yeah, we said we don't care about the L flag, so it's a 64-bit thing. I didn't talk about the L flag. All right, Dave, are you back? Okay, downloading? All right, so we'll have to try to catch you at the next one. All right, so just now to speak a little bit about... All right, so we're starting up again. I don't know if we're going to be playing that in turn time, but it's not good. So we know now that segmentation is, well, we know it covers all of memory, right? And I said that's Linux only knows, as far as I've ever seen. Check Mac, but US support it now, so that's some good news. So, all right. So why even bother learning it, all that, right? If we said that, for security purposes, it's great. You can set, code to be non-writable, and you can set data to be non-executable and stuff like that. Oh, but nobody uses it. So why do we care? Well, because it affects the other parts of the system, right? We said that when we were really getting into it, the point was, let's nail down what it means to be ring 0 versus ring 3, right? What it really means is things like, at the crux of it, is your CS currently set to 0? For the RPL field, the lower 2 bits of your CS register, is it 0? If so, as far as all the access control things go on the system, you're considered to be ring 0, right? And why do those access control things matter? Because if you're user space code and you have it set to 3 right now, it's all those access control things which make it so that you can't just jump into the kernel code, so that you can't just read and write through kernel code necessarily. Although we think that with the current segmentation layout, you can probably read and write. I will check that. But yeah, it also then affects, so when you need to know the fact that in reality, you're always dealing with logical addresses. So I can say now, well, let's see, since this won't be open, I can say now that, we'll wait till you're, but yes, knowing that you're always dealing with logical addresses, whether you like it or not, knowing that the hardware is always using CS or SS unless you override them, that's important, right? And it's not knowing that led to a vulnerability recently that we sort of found with interrupt handling and how rootkits could potentially hide their interrupt changes to the interrupt descriptor table because programs which were checking the IDT weren't actually understanding it's a logical address, not just, hey, it's a 32-bit offset in the IDT. That's the address that's going. Yes, that makes sense most of the time. So most of the time, you're totally good with assuming that, hey, Windows always uses a base of 0, and therefore 32-bit addresses give you a linear address. It's all good. That's just how it works. But the issue is, what if someday your base address in whatever segment you're pointing at is not equal to 0? Right? We already saw one case where that's the case, right? FS, that place where it's like the base address is pointing at a data structure. Well, what if I'm, maliciously changing base addresses, maliciously changing segment selectors and stuff like that? So we found a problem with how some tools work because they didn't know about logical addresses, essentially. And most people don't. I didn't, really have a good handle on it before I dug down into it for this class. Right? So half the material in this class was just me wanting to know stuff better. So I said, yeah, I'll teach you about that. So I have to learn it before I know to teach it. All right, so, and like it says here, it's good to know how stuff works as detailed as possible. As far as key thing is, segmentation is required. The GDT is required. You always must have these segments, at least to that, base level of 0 to FFFF. In x64, segmentation has mostly been removed because Intel looked around and said nobody's using it the way we intended. So we don't need, multiple privilege levels. We just need 0 and 3, right? So they essentially, it's my understanding, they went down to 2 privilege levels, kernel space and user space, because no one was using anything else. They got rid of some segment registers, so they kept GS and FS because other operating systems were still using it, right? Windows was using FS, Linux was using GS, so you still got those, but I'm pretty sure ES and FS went away, for instance. You got code, you got stack segment, which we said is really all of the data segment. And then you've got FS and GS for Windows or Linux as little special data structures that they like to store based on those segments. So there is, some possibility to use segmentation for memory protection as per its, sort of intended use. One, back to that initial picture, para-virtualized system, right? You can have a set of segments which say this is, instead of saying, kernel goes 0 to FFS maximum, right? You could say, well, up there, in the top range, or down there in the low range, you say this is the segment which is Zen, right? Zen is right here. OS, you can pretend you have the rest of it and all that stuff. And that way, you can say if your OS is at ring 1 and your kernel is at ring 0, it's like the OS your OS is at your OS kernel is at ring 1 and your hypervisor is at ring 0, no longer can the OS, scribble all over the hypervisor, right? That's one way that you could use segmentation level protection to protect the hypervisor. In reality, when they added, so the point is Zen came out when they didn't have support for hardware-based virtualization. And so when they went to hardware-based virtualization, people talk about it as if it were ring, quote, -1, right? Because really what it has is ways that you can limit it so that the OS cannot mess with the hypervisor, right? And so it's conceptually the equivalent as if you added a new ring -1, put the hypervisor there, instead of putting the hypervisor as 0 in that one movie picture. So it's So you could do it with something like para-virtualization, but then you have to modify the OS. And so because they don't want to modify the OS, the hardware added this new functional ring for the hypervisor to live in so that the OS could still say, I'm ring 0. Right? But the hypervisor could intercept things like CPU ID instructions, UTSC instructions, and whatever else. Right? So this is where Rob pointed out he was working on a Google native client, which is a very interesting project. It's a way to try to blend the performance benefit of having native x86 code execution inside your browser for browser plugins with having some protection. So the issue is we already have native code execution in browsers. It's called ActiveX. And it's a known security problem because Windows is just dumping DLLs. Anyone who asks for it, oh, pulling this ActiveX thing, it's really pulling in a DLL. Accessing code that's just native, straight up x86 code. It's a standard DLL binary, and therefore, there's buffer overflows and there's all sorts of problems, right? So ActiveX for a while was a very active avenue of exploitation, right? They added a bunch of hacked on other things to try to put access control on top of ActiveX to try to limit all the exploits. Google Native Client is trying to instead sandbox a plugin. So the plugin can run straight up real x86 code and have all the performance benefits over something like Java, right? Java, you're interpreting your code, it's slow. You want to run full straight up binary, but you don't want it like scribbling all over. If there's an exploit in that, you don't want it to scribble all over the rest of the browser, right? You don't want it to be able to go pull, credentials from the browser's credential cache or something like that. Right? And so the point of native client is they're basically using something called software fault isolation, which was originally proposed for RISC-type architectures where you have, fixed instruction sizes and stuff like that. It's very easy to analyze. What they do here is they say, we'll let you run native x86 code as long as it's the code we compile. And the code that we compile, and when our compiler spits out, our compiler will take standard C code, but when it spits out assembly, the assembly is such that we can analyze that assembly and we see that it never accesses outside of a certain sandbox, right? It's incapable of generating instructions that access outside of the sandbox. And how they implement that sandbox is with segmentation. So they're saying if this, if the segment is based at this and offset at that, we make sure that all of these things are segment relative sort of thing. So like, I've got my own little, let's pretend it was in the ES segment or something. I don't know the details on that. Let's say you're saying all of the code which accesses, for this browser plugin, everything is, maybe it's overriding it so that everything is in the ES segment. And so when it tries to access some other memory, if it's in the ES segment and, the rest of the browser is just in your normal CS segment, that means that, it can't access outside of it, or the hardware says, nope, sorry, that address is greater than, base plus limit, hardware fault, right? General protection fault. And so that's kind of how they're trying to utilize the segmentation a little bit. And it's really just an optimization trick. They could implement, assembly instructions around every data access, which, first sanity check the address being generated to make sure you can never create an address that, accesses outside of plugin range. But really sort of the point, if you look at how they've done it on x86 and if you look at how they've ported it to other things, the point is they try to take whatever's available from the hardware and get their, sandboxing with the memory. So early in the year, I showed like a talk from, I think it was Unix Security this year. And, yeah, it was Unix. Where they were just saying, here's how.
Hey, Dino?
Yeah, go ahead.
Two questions. One, is it possible that you lost a microphone because you sound a lot weaker than you did earlier? And two,
How about now? Does it sound okay?
Yeah, much better.
I think it was just falling to the side.
And that kind of protection, won't they still be able to reach all the DLLs that are loaded into the binary and wreak whatever havoc can be done through them?
Well, it depends, right? So I said that if this thing is, right, so we know that yes, all of the DLLs and, the actual user binary and stuff like that, we saw in the life binaries code, right, those are all in one memory space and stuff like that. And we'll learn more about memory spaces on the next section about paging. But the answer is, it should be the case that, for each of these, if each, plugin is, for instance, made as a NACL DLL, the point is, if this thing is, all of its accesses must be in the ES segment, then, well, then it gets into implementation details. Then maybe the NACL thing, when you're like letting a plugin run, you have to like, you swap out the other stuff out of the ES segment. And you're saying, this plugin is running right now. This is the only code over which the ES segment goes, right? So you can move where this segment is. Each time you're going to run a new plugin, you say, okay, now this code is running. Go ahead and set the base to the base of that plugin. Set the limit to the limit of that plugin. And in that case, no, it would not be the case that they can just, jump around and get everyone else's DLLs, right? For whatever code is running in plugin stuff, it can be, sandboxed between these ranges. If you try to access outside of your DLL's range, you're going to go ahead and get hardware fault.
Yeah. So you said that they were pulling out support for segmentation in x86 64. None of the things that you listed sounded like they would interfere with this sort of thing, but is this going to become obsolete?
Well, I believe, I don't remember the details anymore, but I'm pretty sure that one of the points of this talk earlier in the year that we showed was one of the architectures they were showing. One, they were showing ARM. They were showing, hey, we can do the same sort of thing with ARM, and we only need these couple of instructions which like chop addresses so that you can limit it within a certain range. And I think the other one was that they're showing porting it to x86 64. So I'd have to go back and look at the details, but I'm pretty sure they found, some means by which to still get some help from the hardware. But I don't know if it's full segmentation or not. I'll have to check that. Go check the LunchCon archives, and I'm pretty sure, yes, you can still access them. They're on like Adam Pennington's streaming server, and so you can stream them on demand, and you can pull this Unix thing. Was there another question, Willie, that you had besides? It was just the microphone, and then can they, scribble all over the other DLLs, right?
Yeah, I'm good.
Right.
Thank you.
Good. So yeah, that was an interesting point, and again, you can't really appreciate that if you don't understand segmentation. You can't appreciate the elegance of swapping around these different segmentation limits, and that's why the segmentation was there in the first place. But hardware features, use it or lose it, and they lost it. So anyways, miscellaneous. We already talked about this. Windows uses FS. If you access FS0, you're accessing the first element of a data structure that Windows always maps into each of them. It's the thread environment block. And yeah, this is actually where Christina John said went ahead and dug into this for me and showed that yes, GS is some special data structure on Linux. just for your own edification, I will quickly show that data structure. You do, well, you don't use name. That's first of all. First, you set name to Google.
You know, Bing gives you the same results.
Yeah, that's true. But I don't want to be supporting them. Then you go to manage search providers and you literally delete Bing. And then you do site:/open RCP. 4 areas, file type PDF. Then there's only like 6 PDFs on this website. So Windows memory layout. So if you're ever curious, the reverse engineers have to see this sort of thing. This is the nature of the data structures. On the site, it says what it's trying to say here is FS0 always points at this data structure called the tab. And the tab is this big old thing over here on the side. So if you're accessing 0, you're accessing the tib, which is the environment block. And if you're accessing, FS of 1C, then you're accessing this and whatever else. And so the point I had said before is that, like, the virus code or exploit code, it'll say, oh, I know that there's always this data structure at FS0. Go there, go to offset x30, find the PEB, the process environment block. And so it says tab points at PEB somewhere. And then the PEB is over here. And so you can then go to, some other offset. You're just dereferencing pointers and wandering around. And so if you go over here, there is something like that's bringing to mind whatever. There's a linked list in here somewhere that is eluding me at the moment. Where that linked list is the linked list of here's all the modules loaded in my current memory space and stuff like that. The point is, the OS is exporting this data structure to each process, and they each get their own data structure and stuff like that. And that way that, the libraries and stuff can try to find other libraries. Things like that. So anyways, that's just a miscellaneous. So Linux has something similar based at GS. Right? All right, so why isn't segmentation widely used? There can be many speculations, like why, if Intel had this in there, from pretty much the beginning, why did the OS manufacturers not make it? Well, one speculation would be, it's performance versus this. So every time you're doing inter-segment jumps, you've got that extra privilege level checking and stuff like that, right? So if you're bouncing around between segments, you got that extra stuff, so why not just, have it always be within the segment, and you never have to check if your CPL is less than or equal to the DPL and stuff like that. That's one thing. Two thing, with only 6 segment registers, you can't have, we saw that you can have like a ton of different segments. You can have like, 8,000 in the GDT and 8,000 per process, right? And so that would be great. You could like map segments to like every specific, binary section, like we talked in the life of binaries, right? You got that text, okay, code segment. Data, okay, data segment. R data, okay, read-only data segment. Yes, we have, read-only data segments and that sort of thing. Stack, okay, data segment, expand down, right? Problem is, you've only got 6 segment registers, right? And so that means you would have to be swapping in different sort of segment registers into active use every time you, potentially go over, 6 things. And that kind of segues into the next thing of that, maybe it makes the compiler, it definitely makes the compiler's job more difficult, right? So how does the compiler know what the conventions are for your OS so that it spits out the right assembly code so that when you're about to access the RData section, it knows, which segment register to put that into and stuff like that. Right? So how do you get the right code? And if you want generic code, which, works across different OSs, or if you just want to play it conservative and it wants to, be very careful with how it does, then maybe it's like, maybe there's some mapping in data of like, here's this address range, it has to be this segment and stuff like that. And it just, you can see how it very quickly increases the complexity of figuring out how is this OS using segments, how do I need to generate code for that. So, and yeah, speculation is it's all of the above. It's many reasons. I would say it's also, I guess, the first thing I said is, it's probably a lot of the case that, the first OSs when they're being built, the first, think of it more like COTS type OSs. When they're being built, they're not like particularly emphasizing security, right? At the, kernel level versus user separation, they're trying to do some of that. But it's not like Multics where they're, like giving you 8 privileged rings and they want, high granularity and special enforcement. And this isn't, meant to be some high multi-level secure operating system, right? You got DOS and you got Windows coming out and they're like, put features in, get, more people to buy stuff, right? And so what was the point of incurring this extra complexity when, they weren't particularly overwhelmed with the security attacks which came later? So many speculations. I don't think there's any one answer. It's the case that we have 0 to FFFFF for everything. But certainly it says there, right there in the manual, if you want to use flat model, here's how you do it. All right, so this was the miscellaneous I mentioned before when I was talking about LDT, GDT, stuff like that. No pill was in reference to blue pill, which we'll learn about when, or red pill, when we learn about the interrupt scripture table. No pill is basically checking the LDTR register, and it's operating under the assumption that, for a Linux system, it should have, they'll like always be using this LDTR value. There's always some index into the GDT, which is the LDT. And what they found was that in virtualized systems, for whatever reason, that segment selector is different. It's selecting a different location.
So are they not actually 0 in Linux?
That's what I'm assuming based on this. Unfortunately, it doesn't like show any kernel dumps or anything like that. So, but based on this, yes, I'm assuming that the LDT is non-zero, that it is used on Linux to some degree. It may not even be like switching it around between processes. Maybe they just put it in there because the Linux kernel developers were reading the spec and they said, oh yeah, maybe we'll want to use LDT someday. Let's just put in this stub implementation. I don't know. When someone gets a Linux kernel debugger set up for me, I will investigate these sort of things. So please get a Linux kernel debugger set up for me, give me some instructions, and I'll look at it. But until then, I have no need to investigate it to make sure it works. All right, and then this other thing, ScoopENG has a bunch of different things, LDT checks, GDT checks, IDT checks, as we'll see later. So this no pill and red pill were sort of like things which are focused on one sort of virtualization detection, but if you want something that does many different checks, ScoopENG would be great. All right, so here's our miscellaneous instructions we came upon in this section. CPU ID, right, feature identification, tells you what's available on the CPU. Push FD, pop FD, we're pushing the full D-word size E-flags register onto the stack, popping it back off. We said that some of those flags you can't actually pop back off of the stack. Those are going to be set to whatever they were. Those values just won't be overwritten when you do the pop FD. But we'll see later, some of those things, they can only be set, for instance, by an interrupt return. So that, again, gets to that notion of interrupt returns can maybe do some stuff that, you can't move into the CS register, but you can interrupt return and change the CS register. You can't pop FD certain flags in the E flags, but you can interrupt return and change certain flags in the E flags. All right, and then there was just store and load, and, those are ambiguous names, and I can never remember which way is which, but pretty sure based on my visual memory that store is taking the register value and taking from memory and putting it into the register. Load is just dumping it out. No, I can't be right. It's the opposite way. I know it's the opposite way because I know that later it's the SIDT instruction that red pill uses. So, yes, I really should put those in the same order as my pictures. But anyways, point is, one of them is privileged. You can't load up those registers from ring 3. You must be CPL 0. But the other one, you can dump out the register, and that's what leads to these virtualization detections when, for whatever reason, in the virtualized system, these, hardware registers, they're virtualized, right? A virtualized system, if you've got 2 OSs running, you can't export directly to them the same register, right? So they're really just virtual registers, and that's what leads to the difference. So, questions about segmentation thus far? Going back to like some of the early pictures, we'll now maybe make a little, well, heck, I could even go all the way back to here if we really wanted. Let's see, let's see what we've seen of this so far, right? Well, we know the E flags register. We haven't seen control registers, but right here's the GDT. What I was trying to say is there's a segment selector which points at some segment in the GDT, right? And there's this big array. And yeah, there's this GDTR as well, right? This points at the base of the GDT. And so we've got sort of this picture, and we know that these segment descriptors in here, they could point out to a code or data segment, point at TSS. I haven't learned what that is yet. But yeah, the point is, we know at least right now it can point to a code and data segment, or you could have in the GDT an LDT descriptor, which points over here. That's kind of a weird way of putting it, but the LDTR gives you an index into the GDT, which specifies this, and this actually specifies the base address of the LDT if it were being used. And then, your segment selector would have, if the table indicator says I'm checking the LDT, then the index would actually be used to index into the LDT. Yes.
I do know that this one has the call gate only in the LDT. Are those normally?
No, that can go anywhere.
Okay.
All right, so this is what we're going to be learning next in paging. All right, but any questions on, general logical addresses, segmentation, that sort of thing, names, privilege levels, that sort of thing? All right, anyone on the phone? All right, someone's typing, Jessica's typing. All right, no questions. All right, then we are going to move on to paging. All right, so this is on every slide. Every deck, rather. Paging. All right. So we said before, we were pulling the wool over your eyes. We said always logical addresses point to linear addresses. Linear addresses are really just physical addresses. And that can be the case at some point early in the system boot, before the operating system turns on paging for its convenience. So early in the system boot, if you've only got 256 megs of RAM, you better only be accessing things less than 256, whatever 2 to the 56 RAM is in whatever notation. I'll leave it at that. Anyways, because of this limitation, right, for most of, Intel's history, you did not have 4 gigs of RAM, right? And so there's the desire, though, to be able to expose this 32-bit address space so that you could pretend like you could access anywhere, you could space stuff out, have, nice conventions and whatever. You wanted to pretend that you could access anywhere while still only accessing a limited amount of physical memory. But you want to, trick people into thinking it's unlimited, and that's how you have things like, if you run out of memory, you stick it off the disk. That's called paging out. Or, yeah, sometimes they call it virtual memory. We definitely don't want to use that term because it'll be overloaded here. But, when you run out of physical memory, you page it out, and then you still have enough physical memory, and it still looks, magically like you just are accessing virtual memory as much as you want. The whole point of paging is to sort of expose a lie to the operating system or the user processes so that they look like they can access anywhere in this 32-bit linear address space. All right, so when paging is disabled, you got a one-to-one map, linear to physical. When paging is enabled, linear addresses must be translated. So you go through some translation tables, which were covered up. You take a linear address, you translate it through some tables, and that eventually leads you to a physical address. So you no longer have to have a one-to-one mapping. Low addresses in virtual memory can map to high addresses in physical. High addresses in virtual can map to low addresses in physical. And that's really the point, actually. High addresses can map to low addresses in physical. Or when you didn't have enough net RAM. All right. So the reason it's called paging is because of sort of an analogy of accessing information like you have a library. So the analogy is basically books in a library. So when you want to find some information in the bad old days, you went to a library, right? And in the library, there were many books. And so you went to the library, you said, you're going to go to a card catalog, and you're going to say, where's the book that I want to find? It's on this shelf over there. When you get to the book, you now have to once again do a lookup. You go to the table of contents, and you say, well, I'm really only interested in things about Papua New Guinea. And so you go to the index, and you say, okay, well, this is actually on this page of this book. That's where that information is stored. And when you get onto the actual page, maybe you still even need to access some amount of space into the page to find the sentence which begins the information that you want to read. So that's sort of how the analogy works, but the internet ruined it. Yeah, the point is eventually that sentence or word that you're looking for on the page corresponds to a word which you're looking for in memory. So where's my picture? I don't have my picture. I want to go straight to the picture. Yeah, this is the analogy. We're going to show this thing in a second, but basically when you get into the actual tables, there's going to be a first order table which corresponds to the library. Well, first there's going to be a nerd who always knows where the library is. That's me. Then there's going to be a library. I say, the library is over there. And you say, okay, I'm going to go to the library. In the library, you go find the book. In the book, you go find a page. And from that page, you have some offset in that page is the word of data that you're looking for. So that's a preview of what this analogy is all about. That's the terrible truth. All right, so as I said before, this class we use all of the following tables. I just referenced, like, here's the section in the manual where you find this information if you want to look for more detail. But these are all assuming 2008 manuals because I like the pictures and stuff in there better than the 2009 and greater manuals. Terminology-wise, I may refer to frames or physical frames. Sometimes, if I'm being sloppy, I'll say page frame or something like that. A frame is just a chunk of chunk of physical memory, which is the same size as a page, which is a chunk of virtual memory. So the point of pages is that the page eventually maps to a chunk of physical memory, which is a frame. So frames are however big chunk of memory, and I'll just say right now, pages can either be 4 kilobytes, 4 megabytes, or 2 megabytes. 4 kilobytes, 2 megabytes, or 4 megabytes. And each page maps to the same sized frame. So if we're talking about 4 kilobyte pages, we're talking about 4 kilobyte frames. Just physical chunks of memory is what a frame is. All right, and now once we start talking about paging, we rarely refer to linear addresses except when we're going back and thinking about segmentation. So what we say is that this entire 32-bit linear address space is actually now going to be called our virtual memory space. When when you're in some debugger and I say go to virtual address whatever, it's because, whatever segmentation is happening in the background, right? Normally, you've never known or cared about whether the CS register is pointing at this or that segment, right? Because they're always based at 0. So for whatever virtual memory address you want to get to, it's actually a linear address. It's actually, you're actually accessing 32-bit offsets into a segment based at 0. So this is the terrifying truth. This is how the memory access hardware on Intel x86 is actually working, right? So you're always starting at a logical address. Whether you like it or not, whether you know it or not, you're dealing with logical addresses, either explicit or more likely implicit, where the segment selector is always implicitly CS if you're accessing code, jumping, returning, calling, or SS if you're accessing data. Right, so that's always implicit, but when you say, you want to access data at this address, that address that you're accessing is actually just an offset which gets added to the base of whatever CS or SS is currently pointing at. So we already know that. We already know that, this base address is actually always 0, and the limit's always up, so it covers that entire 32-bit address space. But now, this linear address, which we're now going to call a virtual memory address, had this little thing here saying, hey, there's some page here. Right? They're saying this between this dotted lines is something they're considering a page. They're saying for any linear address you want to access on that page, in order to find out where that virtual address corresponds to physical RAM, physical frame, you need to go take that linear address, break it up, like is shown here. You essentially treat your 32-bit address like it was a little data structure. You break it up, and you take the top bits, and you use that as an index into a page directory. Take the middle bits, and you use that as an index into a page table. And then you take the last however many bits. And so once you've got past the page table, it's pointing at, see here again, we have these dotted lines. It's saying this is a page, but we're going to call that a frame, right? So we said here was a page over here in the linear address space, and it mapped over to a physical frame in the physical address space. And this offset is just used to offset into that physical frame to get the word in the page. So this overall thing is a page, but the actual place you're trying to access, you're accessing 4 bytes or 1 byte, etc. That's a specific word or byte.
Can you just refresh me? It's been a long time since I took operating systems. So the linear space is 32 bits in size, and it's 32 bits wide, right? So like a linear address is 32 bits. And this, or a 64 in a 64-bit system.
Yes.
And then the directory and table are also 32 bits wide?
Yes, but we're actually going to see a bunch of variants on these directories and tables. So there's actually sort of 4 different combos of directories and tables. So yes, in OS class you deal with one, but here we're going to at least give you a brief introduction to all of them because in real operating systems you see all of them, depending on how you boot your phone. All right, I'm suddenly extremely sleepy. And I'm sure you are as well. All right, so this is the basics of it. There's going to be some new tables we need to learn about. We need to know what each of those entries are in those tables and stuff like that. But the main point here is like when we're dealing with GDTs and segments and stuff like that, we're dealing with tables of data structures, and we're using some indexes into those tables to get to a specific entry in that table, and that entry has a descriptor, or it's just called entries in these cases, and that's a data structure, right? So when we're dealing in GDT, right, you index some amount into this table, and you've got a data structure, and that tells you something about segments. When we're dealing with paging, you use those chunks of your linear address to index into this table, and each of those will essentially get you one physical address closer to finding the final physical address that you actually want. All right. So, as it says here, when you turn on paging, we saw in that state diagram before, right, there's just one bit you set in the control register, and all of a sudden, paging is considered to be enabled. And the key point about that is that before you turn on paging, you definitely have that one-to-one mapping of linear to physical addresses. After you turn it on, the OS, was, setting up these tables and stuff like that. So part of the OS's job, although the hardware walks all these tables, you'll see that sort of a common thread here is that the OS set up to GDT, for instance, right? The OS said, I want my base to be at 0 and my limit to be at FFF. So there may be hardware registers that point at different things, right? There's a hardware register that says, here's where the GDT is. But the OS has to set up everything about that table. The OS even sets up the value in the register. So OS sets stuff up, hardware knocks it down. And so the second you turn on paging, you better have those tables set up, because otherwise, every time you try to access a memory address, it's going to be trying to walk some tables anyways. And if these aren't set up properly before you turn on paging, and you try to access some memory address, all of a sudden the hardware is going to try to walk those tables, and it's going to, just fail miserably. Unless you get lucky, and even if you get lucky, you're going to get junk data. So again, OS sets tables up, hardware knocks them down. And by that, I mean that after things have been set up, it's always the hardware's responsibility to lock these tables, cache data as appropriate, so that when you try to access some specific logical address way back at the beginning, it all works out and you get the right physical address out of RAM to get the data that you actually want. And so this part is definitely going to get complex. So we're going to review this again, starting from the beginning when we start up tomorrow. So don't worry if you're starting to fall asleep and you can't catch this all. We're going to go over it again. And even when we had OS class and had to learn this to write our own OS, it was definitely the case that it takes quite a while to actually really get it. So even if you think you get it today, you probably don't get it, and that's fine. The point is, like all my classes on, what was it last class? Putting you in a headlock and cramming information down your throat. So all of these things do require a little bit of outside study to really, really have it click in your brain. All right, so ways to translate. This is these 4 combos that I was just talking about a little bit ago. In the traditional way, the way that you're going to learn about in any typical OS class, if it's a good OS class, so I had my undergrad OS class was not so good. In grad school, I took the CMU undergrad OS class, and that was very good. We had to learn all this page table stuff in order to write our own OS and stuff like that. But anyways, even in that sort of class, you only deal with one thing, this first one. You got 32-bit address space. They don't even tell you about segmentation in the class. They just set up those maximum 0 to FFF. Maybe that's the reason why no one ever uses segmentation, because in their OS classes, they always got the simple case of 0 to FFFF. So anyways, you got a 32-bit linear address space, which maps to an assumed 32-bit physical space. It should really say like a maximum possible 32-bit space for physical. It's, whatever, however much RAM you've got installed, that's your physical address space. And you assume that 4 kilobyte pages. So frequently, if I say something is page size, I almost always mean 4 kilobytes because that's, what people always think of. So page size chunk of memory is 4 kilobytes. Oh, hey, look, back in segmentation, that granularity stuff, right? We said whether we were accessing stuff in 4 kilobyte chunks, right? So the limit is in 4 kilobyte chunks, page size chunks. All right. Alternatively, there's this notion of large pages, huge old pages, where you could actually have 4 megabyte chunks. And we'll see why you necessarily want big things later on. But yeah, in the typical case, you're accessing 4 kilobyte chunks of memory at the same time. That's sort of the atomic unit of memory management. It's not getting any smaller than that. Atomic unit of memory management. So if you're writing the memory manager and you're in charge of making sure everything works out, you deal in page-sized chunks. Obviously, you can access 1-byte fields within a page, but when you're like setting up tables for this sort of stuff, you're dealing in page-sized chunks. All right, and then the other thing, which is being increasingly used, and I'm pretty sure it's, well, I don't know if it's fully default or anything yet, but most any Windows system you see around here or anywhere else is actually going to be using this physical address extension. That's how you get NX bit later on. For those who know what it is, for those who don't, that's fine. Physical address extension is sort of a hack so that you can have your 32-bit OS, and rather than rewriting large swaths of it, you can be mostly 32-bit, but you can still ostensibly access 2 to 36 bits or bytes of RAM. So it's trying to make it so you don't have to go full 64-bit. Right? If you go to full 64-bit, yeah, you theoretically can access 2 to 64 bytes of RAM, but you don't want to change your full OS, so that's sort of like an in-between step. If you want to access more than 4 gigs of memory, you got some application which only runs on 32-bit Windows and you don't want to change it, so you hope that your OS supports PAE, and in that case, then you can potentially have big chunks of RAM. Theoretically, 64 gigs. As I said before, Roman D had pointed out that actually XP supports PAE, but it only supports it for this NX flag. It doesn't actually expose the ability to ever access more than 4 gigabytes. But some of their server things and later versions like Windows 7 in 32-bit mode, it can actually access more than 4 gigabytes. All right, so again, PAE, there's one case where it's 32 bits to a maximum of 36-bit physical, you can kind of think of it like, and it's 4 kilobytes. And then also then there's a 2 megabyte version, and we'll see why it's 2 megabytes instead of 4 megabytes later. There is another thing called page size extension, PSE36, which is another way to try to get 2 to 36 bytes of RAM. But I don't know that anyone uses it. I'm not entirely sure what the point of it is. I'm sure there's a point, but I've never seen it used, so we consider that the red-headed stepchild of memory management. Anyways, paging in the control registers, great name for a band. Replace paging with your name. Core in the control registers, it's alliteration. And as someone said, if you can get a girl as a lead and you have her stage name be Paige, then it's true. Page in the control registers. Anyways, we need to briefly talk about control registers. So there are 5 control registers, 0 through 4, which are used for paging control as well as some other miscellaneous stuff. So while we're on the topic, we'll mention some major cases for the control registers. CR0 has the PG bit, which, okay, yeah, I always get confused on that. When we saw that state diagram earlier, the PE bit turns on protected mode. The PG bit turns on paging. So you can actually have protected mode without paging, but typically they're always going to go hand in hand. Just like you could potentially have paging without protected mode. Not sure if that actually works, but it may work. Not sure. So CR0, it's just again one of those structures that has a bunch of different control bits and stuff in it. All we care about for now, you can go look up the definition of all of the different bits later on. All we care about for now is it's got a bit that turns on paging. It's got a bit that turns on protected mode. Oh, well, it says right there. Paging requires PE to be set. I'm pretty sure I pulled that out of the manual, so there you go. You can't have paging in real mode. CR1 is reserved and not used for anything in the last 20 years, so that's lame. CR2 stores a linear address that causes a page fault. As we'll see a little bit later, I already alluded to it. When you run out of RAM, you may be taking RAM and you're writing it off to disk, and then, you can reuse that physical memory. But you're going to, like, mark the virtual memory as, like, hey, you can't access this, it's on disk. And so there's this concept of page fault that is used to, like, pull memory back in when you put it off the disk. CR2, when you try to access some memory, which is no longer here because you've stored it on disk, or if you just try to access some memory which is not there because it's not mapped to anything, you try to access address 0 and nothing's at address 0. When you try to access some RAM and it's not in the virtual memory paging tables, CR2 gets the address of whoever was trying to access that RAM. So if I have an instruction running at 401018, back in our example, if that instruction tries to access some memory and that memory just ain't there, then there's going to have a certain type of interrupt, and CR2 is going to be set to the address of the guy that caused that interrupt. So that the OS can either recover from it, if possible, or, kill the process, that sort of thing. So CR2 for now, we'll come back to it when we get to interrupts, but for now, all you need to know is that there's this dedicated control register, which is just filled in by the hardware. When it can't access the memory, it says, that's the guy who did it. CR3, this is going to be the critical one. CR3 is the pointer to the page directory. So we said, OS sets up tables, hardware knocks it down. Just like the GDT, there's a GDTR, which points at the base of the table. With all those paging tables, it all starts at CR3. Control register 3, aka the page directory base register, which I never call it that. Just call it CR3, and you should know when I say CR3, CR3 points at the physical memory where there is a page directory, which is from these pictures before. This page directory right here, CR3 register is always pointing at the start of that table, so that when the hardware is trying to take this top chunk and treat that as an index into the table, hardware needs to know where the table is. OS puts it somewhere and then sets CR3 so that it points at that somewhere. It is actually a per process thing, and I'll probably unintentionally allude to that multiple times, but since you bring it up, it turns out that each process gets its own different page directories and page tables and stuff like that, so that this process can see memory different from that process. So that this process can have something at the same address as that process, same virtual address, mapped through these tables to different physical addresses so that they don't overwrite each other, so that they're kept separate. And this is the big way that the OS enforces process memory separation. It says, you've got this table over here, and you've got that table over there. And it swaps around the CR3 value. When I'm, leaving kernel to go to Notepad, it gets one CR3 value, which points at one table structure. When I'm leaving kernel to go to calc.exe, it gets a different CR3, which points at a different translation table. Does that answer the question? So again, this is why we need to know things like paging. It's like, how does the OS actually stop? We know that back in the day, Windows 95 and DOS and stuff like that, any process can scribble over everything else. Right? That's what led to crashiness, right? Error in one process takes down the system. In modern protected operating systems, they're trying to enforce separation between these two things. We already saw they're not using segmentation. So how are they doing it? They're using paging, and they're giving different processes different views of memory. All right, so CR4 has a couple of things that we care about. PAE, this CR4 just has, one bit where you turn on or turn off PAE. PSE, now this is a little different from, I said there was this, page size extension. This bit PSE has nothing to do with that PSE. Page size extension says whether or not your page tables may specify large pages. So if this is set to 1, then yes, lucky you, you get to use 4 megabyte pages in non-PIE or 2 megabyte pages in PIE. But if this bit is not set and you set a large page in one of those page directories, as the hardware is walking through the table you've set up, it's consulting things like this. And it's saying, oh, look, I see you have an entry that says you've got a big 4 megabyte page. But then it's also consulting, it's got a line coming down out of that bit and putting them together and saying, oh, but you don't have page size extensions enabled? Well, you can't use 4 megabyte pages. Page fault, CR2 equals whoever caused the problem, probably some kernel code or whatever, etc. So anyways, this is just setting this bit gives you the capacity to even use big pages. But if this isn't set and you try to use them, then you're going to have an error. So again, as like an OS designer, you'd have to know what bits you got to set to use what features and stuff like that. All right, finally, did you have a question, by the way? You were giving me the confused, or WTF.
I keep trying to decide whether to ask why we can still turn paging off.
Why we can still turn paging off? You
Yeah.
don't want to turn paging off. You mess
Yes.
up the operating system.
But we've seen all of these different places that say, when paging is enabled. And I've certainly seen places up to a few years ago where I was given the option to enable or disable paging. So why is that still there?
Say a little more context about where you saw that you could
I
enable
don't
this.
remember.
Wow.
I
Yes,
don't
I saw
remember
somewhere
all,
that I
but
can
there's
turn off paging.
But
Yeah.
I know that you've had a bunch of pages that said things like when paging is enabled.
Right.
Which
But that was
implies
back, so that was back in the notion of, let's say paging is not enabled yet, right? And when is paging not enabled? When the thing just reboots. So when you're in
Okay.
real mode, and we just said paging is not allowed, you may not set PG, paging enabled, requires PE, protected mode enabled, in order to be set. So you may not turn on paging until you're in protected mode. That means anytime you're in real mode, you're not have paging on. You've got segmentation specifying how linear it maps to physical and stuff like that.
Okay.
So all that stuff before
this
was
is basically like BIOS.
exactly.
Okay.
So BIOS starts out in
sense.
real mode. DOS starts out in real mode. The CPU gets reset. You're in real mode. Paging is enabled, and they, they eventually turn it on.
I've seen a lot of stuff where they said, like, well, we turn off paging, but what it really means is they just don't move it from certain chunks from memory to disk.
Okay, yes, that's a good point. That's probably almost certainly an example of overloaded names for stuff. When they're saying maybe we turn off paging, yeah, and that's a good point. There's, for instance, in kernel memory, you can allocate memory, what's called, non-paged memory versus paged memory. And all that means is whether or not it can be paged out to disk. So it means there's some memory which you're going to set, like, you may never kick this out to disk because this has got to be there. There's other memory where you say, yeah, that's pageable. If you need more physical memory, go ahead and kick this out to disk. So that's probably the kind. That's why I was asking for the exact.
Is probably the
Exactly.
yeah.
It's where exactly you see that. You almost never turn off your paging. And that was a lesson we learned in like operating system class of like, you set up your page tables and stuff and it was all nice and direct, physical to linear, and you're like, yeah, I know where my page tables are. When you turn on paging, all of a sudden, the same linear address does not correspond to your physical addresses where your page tables are. And you get all confused and, you want to just like turn paging on and off. It's like, when I got to access my page tables, I turn off paging and I manipulate them and I turn it back on. And like this has like a ton of context switch overhead if you're like bopping in and out, and so you fail if you do that. So you have to do it the right way, which we'll see the right way in a little bit. Anyways, back to PGE bit in the CR4. Page global enable enables this concept of global pages, which we'll see a bit later, but basically it has to do with, there's some pages when they get cached, so I said most table access sort of things we're going to see the hardware is going to cache it somewhere. Later on we'll talk about this cache for these mappings of virtual to physical addresses. If something gets cached, a mapping from virtual to physical, that cached entry can be marked as global or non-global. When it's global, if you're switching around between processes, like I said before, with the CR3 changing up, if I move from one process to kernel, and there's some mapping which is not marked as global, all non-global entries get kicked out of the cache whenever you move between, whenever you set CR3 essentially. So if you set CR3 on every context switch between user space processes or between kernel and user space, every time you're moving between contexts, you set CR3 to that guy's virtual memory address space. If certain address range mappings are not marked as global, they just get kicked out. And so to move ahead a little bit, for instance, you might want to make it so that all of the kernel memory mappings are marked as global, so that everyone has the kernel memory in their memory space, in their virtual memory space, so that when they call a system call, for instance, right, you call from user space to kernel, it executes its code. You don't want that to necessarily, be in some completely different virtual memory space and have to like swap between them. So oftentimes, I'd say almost always with the kernel user space separation, the kernel code is technically mapped into virtual memory in the same virtual memory space as all the processes. And it's marked as global so that when you pop back and forth between user space and kernel space, when user space inevitably needs to call an open file or whatever, when you pop back and forth, you don't want to evict those cached entries. And so this global thing is like, let's take some memory, mark it as always cached, and then that way, when you go back and forth between two different contexts, it doesn't get kicked out of the cache. So PGE, yes, it will pretty much always be on for performance reasons. But again, just to be clear, like the PSE, this PGE in this control register just says whether or not you can even use this global capability. Later on in those entries, those will say whether they are or aren't using it. But this is just like cannot even use it. And so, yes, it's almost always going to be just on because for performance reasons, that's why you have it in the first place. And so we're going to come back to each of these sort of flags, make reference back to these later on, and also one other which I haven't mentioned yet. Once we get into the actual details of how those paging entries look like in the directory, page directory, page table, and stuff like that. All right, so two extra miscellaneous things right now. Let's see where I am. Right, yeah, we'll go through that and then we'll take a break. All right, so accessing the control register, we just saw there's a bunch of those control registers. We saw they've got some bits that we as, pretending we're operating system writers, we want to turn on protected mode. We want to turn on page global. We want to turn on the ability to use large pages. So how do you do that? Well, there's technically just, it's technically its own move instruction. It's different opcodes from your normal move. And there is only register to register sort of moves. So you have a normal register. R32 here means like EAX, EBX, ECX, right? So EAX into control register 0, control register 1, etc. Not control register 1 because it's reserved and not used for anything. Not control register 2 because the hardware automatically sets that to the page fault address. But for 0, 3, and 4, you can say, move, take some value, set it in EAX, do your bit manipulation to set the PSE bit, and then move that over into the control register. So I'm going to put stars on these as if they're new versions because they only have register to register versions and they are different opcodes. All right, so finally back to this. This is what we'll dig into next, but again, these tables are always based at the CR3. Control register 3, always, in every context where paging is enabled, must point at the tables which the hardware is going to automatically walk whenever you try to access a linear address. Hardware says anytime you access, it says everything's a logical address. It does its segmentation deal. It gets to a linear address. These linear addresses, when paging is enabled, they're virtual addresses. And what that means is you don't take that linear address and go directly to physical memory. You have to walk this. This is why it's virtual, because it's not this one-to-one map. And therefore, you walk these tables, and how does the hardware know where the table is that you, the OS, want it to walk? You, the OS, set CR3 to whatever table for whatever context. So the kernel has a CR3 that covers, typically, all of the kernel modules, the kernel proper, and so everything in the kernel is not protected from each other. Right? So it's sort of like the process memory space. Your normal executable is not protected from your DLLs. Your DLLs are not protected from the regular process. And why is that? Because they're all in one virtual memory address space. Different processes have different virtual memory address spaces. But within a process, all the DLLs, all the code, all the data, it's all one big virtual memory space. And each of those virtual memory address spaces is implemented by the OS giving that a private set of tables, which it then goes ahead and when it's going to run notepad.exe, it changes up the CR3 to notepads, page table, page directories, etc. When it's going to run calc.exe, it changes up the CR3 to notepad. And when it comes back to kernel, when you go ahead and call into the kernel, it changes CR3 to the kernel's page directory, page tables, that sort of thing. All right, so that's it for now. We're going to take a 5-minute break. Come back, ask any questions if you want, or ask questions now.